So today we are beginning lecture 56 in the optimization series, and in this lecture I am going to discuss about the starting population typically of a binary GA. And again I am Dr. Ranjan Ganguly. Now the first step in a genetic algorithm is the creation of a starting population. So let us look at n number of points. So here you have member 1, member 2 all the way to member capital N. And these are the n constituents of a population. Now each of these members is essentially a design vector. So if you recall, you have points x11, x12, x13 all the way to x1 small n. So the design vector has size x1, x2 all the way to xn, so it's an n-dimensional vector. So essentially you have capital N number of points in the design space. And now if you look at it, when you are doing a binary GA, each of these points is essentially a substring. And here we have selected M is equal to 6 bits, for example. Therefore, you have a string here, you have a string here, you have a string here, and a string here. And we can concatenate all these strings to create a giant string. And that would essentially be your member 1. Member 2 would be another string, member 3 would be another string, all the way to member capital N, which would be the capital nth string. So essentially these strings constitute the population which starts off the genetic algorithm process. So now the question comes, how do we calculate or get these particular substrings? How do we know where to put the 1, where to put the 0? So here this is all randomly selected. So basically we use random numbers to create these strings. So just to recapitulate some of the important points, the size of this population is capital N. The matrix of strings has size capital N into small n, where remember small n is the size of the design vector. That's the number of design variables is small n. The total number of bits in the population would be m into n into n. Bits are, of course, the ones and the zeros. So that's the total number of ones and zeros in the entire population. Now, the initial population is typically created on a computer using a uniform random number generator. Now, when we talk of a uniform random number generator, it basically uses the uniform distribution, which is a rectangular or a constant probability distribution. For example, if you are flipping a coin, the probability of a heads coming up is 0.5, and this is going to be 0.5 throughout. So that is a uniform distribution. If you are dealing with many natural variables such as height of people or the weight of people, essentially you are going to get a clustering toward the mean. So for a given population, the height of a person is much more likely to be 5 feet 6 inch, and there are going to be very few people who are 6 feet 5 inch tall or who are 4 feet 5 inch tall. So that is something you get in the normal distribution or the Gaussian distribution. But here we will presume a uniform distribution because we want the random numbers to be spread out uniformly through the system or the design space. Now if you want to generate a random number or a random bit, essentially you start with generating a random number, and you can use some built-in function which is provided in most computer languages, be it C, Python, MATLAB, or even in Excel spreadsheet. And this kind of random number generator may give you a point between 0 and 1. So if rand is greater than 0.5, you select 1, and if it is not so, you select 0. So essentially you generate random numbers like this, and depending on where the random number is placed, if it's greater than 0.5, you put 1. If it is less than 0.5, you put 0. So you can very easily code this as a function or as a subroutine in a computer program, and then you can generate a plethora of bits. For example, let me call rand 5 times, where I'm using this function to get random numbers between 0 and 1. And I have 5 realizations of the random number here. So now if we subject this first one to that test we discussed in the previous slide, this is greater than 0.5, so it becomes 1. 0.18, this is less than 0.5, so it becomes 0. 0.20, less than 0.5, 0. 0.71, greater than 0.5, 1. And 0.34 is again less than 0.5, so it becomes 0. So by generating these 5 calls to the rand function, I can generate this 5-bit substring. Similarly, I can go on with this process and create the entire population completely randomly. Now, the binary strings for each member of the population can then be created, and capital N such strings will constitute the starting population. Now, why are we spending so much time in discussing this initial population and starting population? It's because a good sampling of the design space improves the performance of the GA and in fact all stochastic optimization methods in general. Now, if you have a problem with several local minima, that's a multimodal function, a large initial sample is sometimes useful. And it is often recommended that create a population which is larger than the population which is actually used in the later GA generation. So in some places we demarcate these two populations and say we start with a greater number than capital N and then we choose capital N as the starting population. So in that case, what you do is that you keep the capital N best members in terms of the fitness function for whatever you are going to do in the future, which are some of the reproduction functions. So as a rule of thumb, you could use 1.2n to 2n as the initial population, depending on the computational expense of the function calculations in the problem. Now, this process would be something like a screening test, which is frequently given if there are too many candidates for a particular job. You could give all these people a small written exam, and then you could take the best people to proceed further with your interviews or group discussions as the case may be, or do a reference check. So essentially this kind of thing works out quite well, which we have seen in practice. And most studies in fact recommend that you use a randomly generated starting population, just like I mentioned before. So this randomly generated population helps out in letting you run this code several times and getting a different realization each time. Now there are certain situations where random sampling can result in too much sampling of one region of the design space. Or it can also result in sparse sampling of a different region. So this problem can be mitigated to some extent by using a uniform sampling of the design space. For example, let us go back to the problem we discussed in our previous lecture. If you remember, we had two design variables coded using 4 bits each, and the decoded value ranged from 0 to 15. So that was the range of the decoded value. Now, if we look at the encoded pairs there, and let us say we pick the pairs which are separated by 5, the number 5. So you could have 0, 0, which would be this substring here. You could have 0, 5, which is this string here, and so on. So each of those design variables could then be represented by this particular coding, and this could be a starting population obtained using uniform sampling. And the advantage of this kind of starting population is that you can see it has created a kind of grid which has sampled the design space in a uniform manner. One more thing you can do is that you can take a complement of the strings to create a complement of the random population. So a complement of a population is created by replacing the ones by zeros and the zeros by ones in the random strings. So I will show you this in the next slide. For example, let us create a random population of 5 strings with 8 bits each. So I have created this random population here. Now instead of going and creating 5 more random string, I decide to take a complement of this population. That is, I replace in each of these strings the zeros by ones and the ones by zero. So let's look at the first case here. This 0 becomes 1, the ones become 0, then I have again a 1, two zeros, 1 and 0. So essentially I have simply taken this string here, I have replaced the ones by zeros and the zeros by 1, and I have easily got this complement string here. Now, the advantage of the complement string would be that it would enhance the diversity in the population by ensuring that each bit takes on a 0 and a 1 value in the population. So it would essentially end up sampling the design space in a somewhat better manner. Now you could also use a combination of some of these strategies to create a starting population so that you have a good sample of the entire design space. So let us say we could use half the population by uniform sampling. The second half could be random values and their complements. Or we could use 25% by uniform sampling, 50% random, 25% complement. So various permutations and combinations of these approaches can be used, and this would result in a better sampling of the design space in most scenarios. So again, we go back to our basic concept that it's always better to start with a pretty large initial population and then prune this to get the starting population. So I could start with the initial population of capital 2n and then prune it to the best capital N values. Now for problems where the function calculation cost is very high, you may need to use a sparser sampler of the design space, and in those cases you may start with 1.2n as the initial population and reduce it to capital N points. Now, even in those cases where the function is difficult to calculate or the function calculation is very expensive, it's typically better to use a combined approach of uniform, random, and complement sampling to get a better view of the design space. Now, a good starting population does provide a head start to the genetic algorithm. It's something very important which you are going to find out in practice. And if you have selected a good way to select a starting population, you are well on your way to discovering the optimal point with much greater rapidity. Now, one thing we should mention here is that the starting population could also be used in the context of a gradient based method. So for example, you could generate a starting population. You could use these as multiple starting point for gradient based methods in exploring the design space. So whenever you have a multimodal problem, this approach may work out very well. And in some cases, if you are not able to get a good starting solution x0 for a gradient based method, you could create a starting population and take the best point in the starting population. That is the point at which fx is the best possible value, and then use the starting point as your x0 to start off your gradient based method. So again, this starting population approach can be used in conjunction with gradient based methods also. Now finally, I would mention that there are many more ways of creating a starting population. For example, you could use response surface methods or the Taguchi type of solutions we discussed in the response surface chapters to sample the design space. So you could use a 2K sampling, you could use a 3K sampling, you could use CCD, you could use FCD, and so on. Now, these would also help you get various points to create a starting population. And I would say if you are using these kind of approaches, always complement it with randomly generated points, because at least 50% of your points must come from some kind of random sampling, because random sampling gives stochastic algorithms their power. And one of the advantages of stochastic methods is that most people typically run their GA code several times. And each time they run their GA code, they essentially also start from a new population. And if this is done to a large extent, then in 10 runs of your GA code, you have a greater chance of getting to your minimum point than you would get in most classical type of methods, where you would need to start from a starting design, which is difficult to obtain, and then you would need to find out the different points in the design space from where you could get the design and so on. So again, we spend some time here on how to get the population, the starting population for a typical binary GA. And in the next lecture, I'm going to discuss how you are going to use this population, how you are going to create mating pools out of this population using methods such as tournament selection. And then also we are going to look at the aspects of mutation and how then we get the next population or the next generation of the population. So I'll see you in my next video.